Okay, welcome back to another 10-minute math. This time we're looking at logarithmic form, and we're going to do this in under 10 minutes, guaranteed. So, basically logs are a way of rewriting exponential statements where the exponent becomes the answer. So for example, you might have 2 to the power of 3 equals 8, which is a statement that makes sense. And if we write it as a log, it becomes log in base 2 of 8. So what happens here? The base over here actually becomes the base of the log. The exponent, as promised, becomes the answer. And the old answer here, what used to be the answer to 2 to the power of 3, that becomes what we now call the argument. Argument. There we go. Okay, so quick recap. The original base becomes the base of the log. The exponent becomes the answer. The old answer becomes the argument. Let's try it out. So here we are. Let's put the following in logarithmic form. So if we're going to write 5 to the power of 2, which is 25 in log form, we're going to first start by writing log. Now, the base becomes the base of the log. The exponent 2 becomes the answer, so leave some room. And the old answer becomes the argument. And you can quickly double check. 5 to the power of 2 is 25. Now this one looks a little bit trickier. So once again, the base is 2. We're going to write a 2 down there. Now the exponent becomes the answer. So that'll be -3. And now the old answer becomes the argument. And we can use some brackets around here. We don't have to. It's optional. But here we go. So we got 2 to the power of -3 is 1 over 8. This one here, we got 6 to the -2 is 1 over 36. So if we're going to write that in log format, the old base becomes the base of the log. Let's do it a little bit differently. The old answer becomes the argument. So we write that in there. And the old exponent becomes the answer. So now we say 6 to the -2 is 1 over 36. Now here's an interesting one. So let's go ahead. So 5 to the 0 is 1. We can all agree on that. So the base is 5, so we're going to write that in there. The exponent becomes the answer, so it's equal to 0, and the argument is 1. Double check. 5 to the 0 is 1. A good job. All right. Well, now that you're a master of going from exponential to log form, how about going from log form to exponential? So let's see what happens. These ones we can always check as well. So the base of the log is the base of the exponent. The answer is the exponent here, and the argument is the old answer. So we can all agree that 3 to the power of 3 is 27. So that one seems fine. So the log base is the base of the exponent. The old answer is the exponent here, is the power, and then it equals the argument, so 1 over 8. So there we go. We saw that one on the last slide. Here we go. 36 is the base of the log and also the base of the exponential form. The answer here is the exponent. So it's 36 to the 1/2, and that equals 36. We can check. 36 to the 1/2 is just a fancy way of writing the square root of 36, which is indeed 6, and we are very happy about that. Here we go, last one. So the base of the log is 7, so that's the base of the exponent. 0 is over here in the power, and it equals 1, and we can double check. 7 to the 0 is 1. That's all hunky-dory. Perfect. All right, now the common log. So if you have a graphing calculator, if you have a non-graphing calculator, they usually work in log base 10. You can get some fancy graphing calculators that can do any log base, but every other log or every other calculator is going to be using the common log, which is log base 10. So much like how when we have a square root and I write the square root of 36, I'm actually cheating and the index is 2. We don't actually write the index 2 in there. If it's not there, it's generally understood to be a 2. Well, that's the same with logs. So if no log base is shown, it's assumed to be a 10. So for example, if I have log 100, you'll notice, hey, there's no base here. That's because it's assumed to be 10. So you can double check. If you write in a 10, it should all check out. 10 to the power of 2 should be 100, and indeed it is. So Now you know, knowledge is power. Let's go ahead and evaluate a couple more logs. So now we're actually evaluating them. So we're given a log and we're going to be looking for an answer. So on the grade 12 exam, be very careful about introducing a variable without defining it. So if I'm going to do A, I might do my work over here to the side and just kind of ask myself, well, 2 to some power has to equal 32. So I'm just going to go 2 to the x equals 32. And then here you're going to have to use your noggin and say, okay, well, x must be 5. Now you can't actually write that on the question. What you can do on the exam is do your work on a separate page and then just write equals. Oh, I don't know why I wrote equals 2. It equals 5. Mubby. There we go. Whoops. There. And I lost my nice calligraphic pen. I want it back. There. Okay, let's do a little bit better on part B here. So again, I'm going to be asking myself 3. So 3 is the base. 3 to some power has to equal the argument. So that's going to have to be 4. So I can just write equals 4. Now this one a little bit trickier. So it's actually, for this one, it's actually, well, the base, the log base, raised to the power of the answer has to equal the argument, which is x. Well, that's easy. 2 to the 3 is 8. So in this case, because there is an x, you can actually write x equals 8 underneath this one. Now, and again, another tricky one. This time the log base is x. So I'm going to be writing x to the power of the answer. So that's -3 equals the argument. And we have seen this one a couple times. You're just going to have to think. Or you can use your knowledge from the last section and say, well, 1 over 8 can be rewritten as 2 to the -3. So now that you have the same exponent, the bases must match. So again, in this case, because there is an x, you can actually go ahead and write x equals 2. So those were sneaky. I'm going to end off with 2 very important conclusions about logs. So let's solve these 2 questions and then notice 2 very important things. So again, in this one, I don't have an equals x, so I just need to be careful that I don't actually write it on the exam. Just do your work on a scrap piece of paper. So I can write 7 to some power has to equal the argument. So in this case, the power must be 1, and we arrive to our first conclusion that a log that has the same argument and base matching is always equal to 1. My English is amazing there. So basically what I'm saying is if the base and the argument are the same, then you are guaranteed that this is going to equal 1 every time. So really quick, if I got log 99 and the argument is 99, without doing a lot of work, I know it's 1, because it's going to be 99 to the power of 1 is 99. Last one. So let's go ahead and solve this puppy. So if I put it in exponential form to try to solve, it's going to be the log base raised to the answer, which is x, equals the argument, and we go, well, this one doesn't make me very happy, because there is no way that I'm going to raise 2 to some power and get a negative number. It's just not going to happen in the real number system. So we say that this one does not exist, and we arrive to a very important conclusion for when we start graphing these things. Log arguments must be greater than 0, okay? So you'll never raise something to a power and get a negative number. So log arguments always greater than 0. Thanks for joining us for a logarithmic form. See you next time. Bye-bye.